let's move on to the subject of today, which is what? It's superposition. What is superposition? I heard of Superman, Supergirl, Superboy, superposition. What is that? Let's find out. Well, we covered the other day, we covered decoherence, okay? And so this is briefly what decoherence was all about. Particle at two places at once. And they always use this slit experiment. You shoot one ball, and the ball is at two places at once at each of the two slits. And then they come together somehow and they make the fringes. So how can this ball be at two places at once? It's not that ball breaks in half or turns into two balls. No, it's the same ball at two places at once, if you can understand that, okay? And the photon is simultaneously both an extended wave and a point corpuscle. That's what decoherence essentially comes down to. Okay, so that's the logic, you can call it, if you can call it logic at all, okay? Okay, then we went on to entanglement. And here's entanglement. These are properties that they found, that they proved in quantum mechanics, okay? And what is entanglement? Well, a particle here affects one over there, okay? Without any physical mediator. There's nothing in between the two particles. And there you can see a little picture of that, a little video there. Clockwise on the left, counterclockwise on the right. You switch them around, and now one instantaneously changes the other, influences the other particle, even though they're not connected in any physical way. And even though, you know, these particles are millions of miles away from each other. So how do you explain this? What's the explanation? They say, it is so. Okay, let's concede. Let's concede. I have no problem. I'll concede. Why? What causes that? And that's where they fail. They cannot explain this, especially with particles. Okay? And so they talk about instantaneous action at a distance. It's instantaneous. You twirl one, the other one twirls in one way. Then they re-twirl it in the other direction, and the other one is measured to be twirling in the opposite direction as well, instantaneously. Okay, so they say. Okay, so this is what quantum proposes. Again, no explanation, it's just a description. They say this is what we observe, and they leave it at that because they only do descriptions. Okay, so those are properties that they supposedly proved, discovered, observed, as they like to say, in quantum mechanics. Well, and here comes the third one, and that's superposition, the one we're going to talk about today. And what do they say? They say in quantum physics, an atom can be excited and not excited at the same time. It's excited and not excited at the same time, simultaneously. Now, does that make any sense to you? Okay, it's a bit scary. That's what it is, because these are PhDs. Okay, they studied 10 years at a university, and they believe in this explanation. They say this is the physical interpretation that we have today. That's that, you know, the particle can be vibrating and not vibrating at the same time. Expanding and not expanding, you can go over and over, just apply anything that you can think of. How can something be vibrating and not vibrating at the same time? What sense does that make? And of course, they don't make any sense of it. Okay, and that's the issue. Okay, and so here's the definition, so that you don't take my word for it. These are, one is from one side, the other one's from the Wikipedia, and these are the definitions they have for superposition. Superposition is the ability of a quantum system to be in multiple states at the same time until it is measured. Then it collapses to one or the other. Okay, and the concept is difficult to understand. No kidding. No, it's not. I understood you perfectly. It's irrational. That's what it is. Don't tell me it's difficult to understand. Tell me it's impossible to comprehend. It's impossible to illustrate, to visualize, to picture. So this is absolute nonsense. You cannot say that it has both of these properties at the same time, that it's vibrating and not vibrating. And then you see the Wikipedia there says quantum superposition is a fundamental principle of quantum mechanics. Okay, great. States that, much like waves in classical physics, any two or more quantum states can be superposed. And the result will be another valid quantum state, and conversely, that every quantum state can be represented as a sum of two or more distinct states. This is their notion. This is what they're saying, folks. Let's get it right. This is the picture of what they're trying to say. Saying that the horse is standing still and at the same time it's running. That's what they're saying. How can you picture this? Well, I tried my best to picture it, but see, even I cannot understand what I put there. How can the horse be running, galloping, and at the same time be standing still? This is what these people are saying. Now, I want you to look at that. Does that make any sense whatsoever? And no, the answer is, at least to my understanding, rational folk will never understand this. There is no explanation. And these people admit it. They say they don't understand it either. Where does this all come from? Well, it comes from really, if you want to trace it back, you'll find it here. You'll find it to these two gentlemen, beginning of the 20th century, Mr. Niels Bohr and Ernst Rutherford, and they came up with their planetary model of the atom. They do it all with little particles. Okay, they didn't have the three quarks in the center then, but that is the model today, and it's a planetary model, and nothing has changed in 100 years. People say, well, no, it's not the same one. It is the same one, because this is the atom that they're going to use for electricity, to illustrate electricity. It's the same atom they're going to use for ionization, and it's the same atom that they're going to use for what you're seeing there, which is the quantum jump. There's an electron falls to a lower energy level, and it emits energy. And when it rises, it absorbs energy. That's that arrow that you see coming into that squiggly arrow. That's the so-called energy. This is the model that people use today to explain those three phenomena. Okay? And again, I always say, why does the electron fall to the center of the atom, which is one of the things that these individuals try to explain. Okay? Why doesn't it fly away spontaneously? That's what you got to explain. The blue ball seems to always be faithful to those rings, and those rings don't exist. Those are known as energy levels, which is a mathematical concept. We have no idea what those are. I mean, are those shells? What are those? I mean, physical shells. What are those things? And they're not. Not according to quantum. So when you look at that, you say, what are they talking? What's a physical interpretation? And you won't find one. And don't take my word for it. Here, I'm going to give you authority. We're going to let the horse, the galloping horse and the static horse speak for themselves. Or you're going to hear it from the horse's mouth. This is Bohr. Okay, this is what he said about quantum mechanics. After, he gave it a lot of thought during many years. These are his comments, okay? So this is what you got to keep in mind. There is only an abstract quantum physical description, not explanation, description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. If quantum mechanics hasn't profoundly shocked you, you're an ignorant fool. You haven't understood it yet. That's what he's saying. It's got to shock you because no one can understand it. Everything we call real is made of things that cannot be regarded as real. This is what he's saying after many years of studying quantum mechanics, researching, etc. Nothing exists until it is measured. So, that fellow that's on the other side of the planet, he doesn't exist because you haven't measured it. You don't see him, you don't touch him, you're not measuring him, so he doesn't exist. That's what he's saying. So you figure it out. Is that a good definition of the word exist? And yeah, this is the way they use it. They have faulty definitions. They throw around the definitions of ordinary speech. They bring them into science casually, and you say, well, yeah, I know what he's saying. He's saying if you don't measure it, then you can't touch or see it, so obviously it doesn't exist. Well, does the Chinese man on the other side of the planet exist? You haven't seen him, you don't touch him, you don't measure him. Does he exist? And you may say, well, he doesn't exist to me. Well, that's too subjective. We need a little more scientific definition of the word exist, something that we can apply in every situation. And that's what we don't have from these folks. Okay, here's good old Heisenberg. This is what he said about quantum, okay, and about all this stuff, all these properties that they allegedly proved and discovered, etc. He says the Copenhagen Interpretation, which was the Bohr-Heisenberg version, which was from Copenhagen, Denmark, where Niels Bohr was from. He created a school of thought, okay, and he called it the Copenhagen Interpretation of Quantum Mechanics, which is really the one that's still strong today, okay, has led physicists far away from the simplistic materialistic views that prevailed in the natural sciences of the 19th century. They would prefer to go back to the idea of what? An objective world. So they're talking. So what is Heisey saying? He's saying that quantum mechanics is subjective. There is no objective world out there. That's what he's telling you, okay? In the experiments of the 50s and 60s, many new particles were discovered with long and short lives, and no unambiguous answer could be given any longer to the question about what these particles consisted of, since this question no longer has a rational meaning. Okay? And that is no doubt the most important experimental discovery of the last 50 years. That it has no meaning. You cannot understand it. They have no explanation for it. The natural laws of quantum theory no longer deal with the elementary particles themselves, but with our knowledge of them. Okay? And really it's got to do a lot with probability, because quantum is a probabilistic theory. They call it theory. It's a description. Probability is description. It's got nothing to do with explaining. So it's not a theory, but they call it a theory. The theory part is the one that they cannot explain, which is the mechanism. That's a theory. That's what physics and science is about. And these people cannot explain it, so they turned mathematics into science. They turned mathematics into theory. They took descriptions, quantitative descriptions, and called those theories. And because they prove or attempt to prove mathematical equations, they talk about proving theories. Okay, so that's how this all developed. This is how it all evolved. Okay, and finally, let's get a fellow who's more closer to our days. He's already dead. It's Richard Feynman, and he puts the icing on the cake 50 years later than, when quantum came around in the 20s. He said, I think I can safely say that nobody understands quantum mechanics. Do not keep asking yourself if you can possibly avoid it, but how can it be like that? Nobody knows how it can be like that. The more you see how strangely nature behaves, the harder it is to make a simple model that explains how even the simplest phenomena actually work. Explains. He cannot explain it. Okay? Describe, they can describe it. They can do probability. They can do all that stuff. They cannot explain the mechanism. That's what he's talking about. So he says, so theoretical physics, mathematics, has given up on that. They've given up on that. They don't do explanations anymore. They do explanations. They give you a mentally retarded explanation. They say, well, yeah, and when you call their bluff, they say, we know it's irrational. Don't try to understand it, and we don't either, and that's philosophy anyways. It's opinion. What's important for them is the math, the equations, and they call that science, they call that physics. That's how this whole thing developed. Okay, so what are my conclusions on, this is how superposition came to be. Okay, so what are my conclusions on superposition? Well, together with entanglement and decoherence, here's a summary of all those really. The physical interpretation known as superposition arises because the mathematicians can't peer into, observe what is going on in the invisible world of atoms. Like I say, so much for observation as being part of the scientific method. I mean, if observation is a key feature of science, here these people are saying we cannot observe the invisible, intangible stuff that's mediating these transactions, these phenomena, then why do they say observe? What are they observing? What are they touching? Well, they observe touch. Actually, they don't even observe or touch those. They simulate them with computers, okay? But because it's too fast, too invisible, too untouchable. And so they simulate all this stuff with computers, and they put little balls in there. Particles, they call them. What are those particles? Equations, just a probability of something being there. And they illustrate that with a point because they don't pay any regards to structure, architecture, body. And so they just simulate those with little balls, and so that you can see what's going on, because otherwise they wouldn't have anything to, what are they going to do, put an equation there and just move the equation around? So no, they put in a little ball and you say, okay, I understand that this particle collided against that one. But they're colliding are equations. Probability of finding an alleged particle in that region, they put the probability, it's an equation, they simulate, they represent it with an equation. That's what they do in their computers. And so they calculate speeds, energy, force, mass, all that kind of stuff, charge, all that kind of stuff, which has nothing to do with physics. We want the physical interpretation. We want the explanation, and they don't have one. And so the question is, what is observation for? What is observation of something you cannot observe by their own reckoning? And then they cannot touch it, they cannot see it. And so why do they say that science is about observing? That observation is an important feature of science when they cannot observe these things. And then superposition is yet another irrational physical interpretation of quantum mechanics, together with the other two, decoherence and entanglement. Okay, and it is not just that there is unexplained, unjustified action at a distance, entanglement. It is not that a particle can be at two places at once, decoherence. It is that a particle can also be vibrating and standing still simultaneously. The horse is galloping and standing still simultaneously. Now that, I think, beats the other two, because a particle at two places at once, a particle being both, a particle influencing another one from a distance, well, those are already quite irrational. But this one, where you're looking at a little particle and you're saying that that particle is at the same time standing still and vibrating, well, I don't know, I think that beats the other two. But they're all very close. It's a very tight race there, okay? When the mathematicians, use the word quantum to qualify computers and dots and all that technology they're developing, right? They insinuate that their theory is correct and has been proved. And a lot of people take it like that because they say, well, why would they call it a quantum computer if they have not proved quantum mechanics? Obviously, the computer the existence of the computer, the fact that you have a computer, you can use it, is proof, evidence that the theory is correct, for otherwise you wouldn't have the computer. That's the reasoning these people have. And that's not absolutely not true. One thing has nothing to do with the other. Technology is one thing, the explanation is another thing. What these people have is a description of something they observed, and they use the classical part of that. They use the part that is touchable and seeable, and the invisible part, they describe it, they use it in computing, like you would use a magnet to collect iron filings. Well, yeah, you can collect them. That doesn't mean you can understand or can explain how the magnet did it, what the physical mechanism is. And this is no different. They're saying, the computer works because we tried it in the lab, we found this effect, and we applied the effect. It doesn't mean that they can explain how Mother Nature does that effect. That's the issue. Okay? But they call them quantum computer. It confuses people into thinking that these people have the right theory because otherwise the computer would not work. That's their tiny mental reasoning. Okay? And this hides the real situation. They can't explain the phenomenon. They can only, in this case, superposition, they can only describe it with using particles which are actually what? Equations. Okay, so that's in a nutshell, not only superposition, but entanglement and decoherence, all in one there. They're all irrational explanations, but that's the only explanation they have. And so this is where we're at today. They call it science.